Hello everyone, this is Prabhat Kumar of Team C9, also known as WinRAR, of The Ohio State University's Fundamentals of Engineering Honors Robotics Competition, and this is the third design update for our robot. If you haven't seen our previous videos, click here to see our first design update, click here to see our second design update, and click here to see our latest testing run and successful performance test. Like our previous videos, this design update is a chance for us to tell you about how our robot has changed in the past week, as well as how our last week of testing has gone. So let's get started. So let's start with the robot drivetrain. As you can see here, these are our two Iguan DC motors, and we've actually started having problems with them over the last week of testing. So if you see our previous testing videos, you can see that during some runs, the robot curves just a little bit, but that adversely affects our robot's trajectory. So this is likely because both of these motors, they don't operate at the same speed. So when the Proteus gives them a certain amount of power, the left motor may go 1% faster than the right one does. And this can ultimately make or break our run. So we need to get to the bottom of this issue. So how do we fix this problem? We want our robot to go straight in order to successfully and consistently complete the robot course. One way is by changing how much power goes to each motor. So if you see our March 10th testing video, you'll see that we played around with different power levels for each motor. Originally, our motors were going at 25% power. However, we changed the percentages for each motor. For example, we set the left motor to 24% and the right motor to 25% and vice versa. However, we found that this was not a good solution. So this approach ultimately failed, as you can only send whole number values to the motors. For example, you could send 24% or 25% or 26% to each motor, but not a decimal like 24.5%. And this was problematic because whenever we changed each motor by just 1%, it would curve in the other direction. So this means that the problem was within 1% of a power difference. So we had to find some other way to fix it. Another thing we tried was reducing the power sent to both motors by the same amount. So we changed the amount of power going to the motors from 25% to 20%. And this made the robot go almost perfectly straight. So this could be because as you increase the power going to each motor, it becomes less reliable, and also there's a greater discrepancy between the speeds that both motors spin at. However, when we tried this method on the actual robot course, it didn't fully work. So we're going to have to try both methods and see which one works. Another reason our robot might not be going completely straight is because of these 3D printed wheel adapters. So I've talked about them in the other videos as well. However, no matter how many of these adapters we get, it is still a problem. So let's take one of these adapters off and see what they are. So this is the 3D printed adapter, this is the wheel. So this is the cone. This hole is for the motor shaft to go in, that's what this is. And what you can't see are the teeth on this adapter that fit into the holes of the wheel, as you can see here. Now, there are a multitude of problems with these wheel adapters, and this is the second replacement pair we've got, so we've ordered 3 of them so far. And because these current wheel adapters are broken, we're going to have to order yet another pair of these adapters. So there are 2 main problems with these wheel adapters. One is with the teeth and one is with the keys. So let's take a look at these blue adapters. These were the first adapters that we got, and they both broke within a few days of testing. So here you can see what's left of the teeth, and here are the 2 teeth that survived. So these teeth on these adapters break very easily regardless of how much torque that the motor puts on it. So this is the first set of adapters that we got. This is the second set of adapters that we got, and you can see that all of the teeth on them are gone. And that is the case for these adapters as well. Many of the teeth have broken off or are in the process of breaking off. Another problem we had with these adapters are with the keys. They are holes that connect to the motor shaft right here. So in the case of the second adapters that we got, not only did the teeth on them break, but also the key, or the hole inside of it, was way too big for this shaft. So for our third set of adapters, not only have the teeth broken off, but also the keys are also wearing out. So whenever the motor turns, the wheel is having trouble turning with it. So we hope to remedy this in the future by ordering yet another set of wheel adapters and immediately gluing it to the motor here. We know that it will make our robot less reliable, but that is the best solution we have so far. So we hope by fixing the adapter issue and the motor power issue, we'll be able to make the robot go much more straight and much more consistently. So this has probably been the most frustrating part of testing the robot, but we hope we'll have this problem solved by the competition. So we haven't made any electrical changes to a robot in the past week. However, we do intend to put a line following kit right here in between our caster wheels. So this line following kit will help our robot capture the lava core much more effectively. And you can see this in our previous testing videos. If the robot is just a bit off, this paw here has trouble reaching the core and retrieving it. However, if we have a line following mechanism, it'll be easier for the robot to make a tiny adjustment to align itself perfectly. So something that has changed drastically is the paw mechanism that was introduced in the last video. So let's start with the servos. So we had to implement a double servo design. So originally, the shaft here was connected to only this servo. However, we need a second servo because we need 2 degrees of motion for the lava core. So this servo makes the paw go up and down. So this helps retrieve the lava core, which goes right here in between these teeth. And this servo helps rotate the paw this way. So what happens is the robot drives up to the core, then this servo activates, the core goes up, then the robot goes to the other side of the course, and then the core is suspended over a box that it needs to be deposited in, and then the second servo rotates the paw, and the core drops into the box. So as I said in the previous video, the advantage of a servo motor over a DC motor is that, firstly, you can program the servo to get to any degree precisely, and it also stays at that degree when the servo is powered. So as you can see, we can tell the servo to go to 50 degrees like this. So let's talk about the paw head itself. So it's the same 3D printed part as last week, however we've made some modifications to it. The first thing we did is file some of this 3D printed material off of the prongs here. So this is to ensure that the paw captures the lava core when it drives up to it. So before, if you saw our previous testing videos, you saw that if the lava core was placed right here, sometimes the robot would not capture it. However, because we have these pointed edges now, the robot has an easier time of capturing the core, and there is more leeway, so as you can see here. Another improvement we made was cut this piece of wood and epoxy to the 3D printed head here. So this is to ensure that when the paw is raised like this, that the lava core does not slide off the paw. So the reason we need to raise the paw this high is to ensure that the robot can still hit walls with the micro switches. Because if the paw was like this, then this would hit the wall instead of the micro switches, and that would affect our navigation. So let's talk about the rest of the paw. So as you can see here, this shaft used to be made out of a pencil. However, we replaced this crude design with a much more sophisticated 1/4-inch dowel rod. So we hot glued the dowel rod to the opening right here, and we also made a little adapter for the Futaba servo, as you can see here. So there's the servo head right here, and we cut a little piece of wood that goes here. We inserted some 2mm diameter screws into here that fit right here, and we also cut a circular hole right here for the shaft to go into. And this was all fastened with epoxy and hot glue. Another thing we did was fasten this servo to the chassis much more permanently. So before, it was fastened to the chassis with duct tape and cardboard. However, we cut 4 sheets of this wood right here and epoxied it to the chassis. We also epoxied this servo to the wood. In addition, we hot glued this servo to this servo. So that ensures that this paw is a very robust structure that will not break with continuous testing. Furthermore, we cut this piece of wood right here to place on the front of the robot to hit the button. So as you saw in the previous testing videos, if the robot hit the button with the servo, it would often be very unreliable. However, we made this piece of wood and then fastened it to the front to ensure that the button is hit by a very flat surface, and that will increase our reliability. The final structural change we made is add these erector sets and the QR code right here. So as you can see, these are metal erector sets that were bent and then also screwed onto the chassis right here. And this is the micro QR code. It is used for the robot positioning system. So that's a way for the course to relay heading and position information to the Proteus. So there are cameras mounted to the top of the course that scan this QR code, identifies the robot as Team C9's, and then calculates the position and heading of the robot, and then relays that information via radio signal to the Proteus here, which can then use that information to complete the course. It's important to note that our group has not implemented RPS into our code yet. However, we do intend to do this in the future. This will drastically improve our reliability because it helps mitigate the effect of wearing out motors and bad wheel adapters by ensuring that the robot is at a certain position when we want it to be. And the final change we made is add these little banners to our robot right here. So they're identification information for a robot because we are required to have something that designates us as Team C9 on our robot. So we made it look good by printing out our logo here and then making a little string banner holder right here and also this flagpole right here. So this concludes our third design update for the video. Thank you very much for watching. I hope you enjoyed the video. If you did, make sure you subscribe to stay posted on our robot competition progress.